Optical activity, the portion we skipped on the current handout. Stereochemistry. Yes. Optical activity, we'll go over this here. Here in the lab. Please be prepared for that. Identify any chiral carbons in the compounds below. Any chiral carbons here? Chiral carbon is the most common site of asymmetry. Can you have chiral nitrogens or sulfurs or other things? Yes. Last page of one of the handouts. Chiral carbon is most common, particularly at the introductory level. Because if we can identify a chiral carbon, we're identifying a site of asymmetry, no symmetry. Now, if there's no symmetry there, that's typically going to ruin the symmetry of the whole molecule. We'll talk more about it. Any site of asymmetry here? Is there a chiral carbon here? No, no chiral carbon. Good? Yeah? Do I agree? Oh, wait a minute. Do I agree? I don't know. I've not looked at it. I don't know. I haven't asked the questions. Everybody good? Good. Okay? But I don't know if you're good. You got to know you're good. That's not a chiral carbon. Why not? Not four different things attached. If you go this way, it's the same as going this way. It's the same path. You end up here. This is not different. Chlorine, there's an undrawn H here. This and this is the same. Any chiral carbon here?
Yes.
No. Not chiral. Which carbon's chiral? Tetrahedral carbon with four different things attached? Four different groups. And by the way, this is carbon, this is carbon. Sometimes students say, well, they're both carbons. Well, that doesn't matter. They're both carbons. Is it the same group? Yes. If you come here, it's the same thing in this ring. Here, that's not a tetrahedral carbon, that's not a tetrahedral carbon. These are tetrahedral, it's not four different things attached, two H's, etc. You think that's a tetrahedral carbon? No, it's true of a planar. A planar carbon has a plane of symmetry. Anything planar has a plane. Plane right through it, that's a plane of symmetry. A trigonoplanar carbon is not, it's symmetrical. A piece of bread, you can slice right through it and make two identical pieces of bread that are just thinner. Assuming the bread is the same on top and bottom. Now my hand, you can. If I slice right through my hand, I'll have a palm on one side and the top of the hand on the other. But this piece of paper is planar, assuming there's nothing written on it. Now because there's something written on it, I cannot slice right through, because I'll have something on the bottom, something on the top. But a plain piece of paper, or the same thing written on both sides, I can slice right through it and make it a thinner piece of paper. Can you get thinner than this? Yes. When you get to atomic level, I can slice through here like a billion times. Thinner, 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 thinner. Okay, there's no chiral carbon in either of these. Chiral carbon here. Yes, right here. Tetrahedral carbon. Four different things attached. Chlorine, undrawn H. Is this the same as this? No. No, this way you encounter the alkene, that way you do not. Four different things. And so this compound is chiral carbon. When you have that scenario, now you can have two different configurations. And we can show those. We can have one configuration where the chlorine is back. And we can have one configuration where the chlorine is, forward. And here's back. And these are different compounds. What's the relationship between these two? These are enantiomers, right? Mirror images. Or they don't look like mirror images. You want to draw the mirror image of that? about that? Are these now mirroring? Yeah? Well, these are the same thing. You can draw the mirror image two different ways. You can draw it as actually a mirror, or what can you do? You can keep the backbone the same and just switch your projection, right? How do we know these are the same? Well, name them. What's the name of this compound? A cyclohexene? Name it. What position is this?
3.
Yes. 3-chloro cyclohexene. Everybody good with nomenclature of alkenes, including E and Z terminology, stereogenic alkenes? Video. All these are 3-chlorocyclohexene, right? What's the difference? What do you want to call this one? How can we distinguish this one from this one? RS. Is this RS? Chlorine's 1. H is back, that's 4. What's 2? Carbon to carbon. Well, we have to look at what's on the carbon. What's on this carbon? Another carbon, and then 2 H's. What's on this carbon? A double bond is counted as if it's 2 carbons. So carbon, carbon, and then the H. Do we have a winner here? No. Do we have a winner here? Yes, this is the winner. Okay, so that's 1, that's 2. The other carbon is 3. The H is there in the back. Is this RS? R. And so you can put an R right here in front of this. Okay, R, name. Is this S? 1, 2, 3. Where's the fourth group?
H, coming straight forward.
4. It's clockwise, but the H is 4, so what do we do? Reverse it. So this is what? That's S. And so that would be called S. Name. Well, what is this one over here? I already told you it's the same thing. Is it S?
Yeah.
Let's do it. 1. What's 2? Here. 3. Where's the H? Back. 1, 2, 3. Counterclockwise. H in the back. I say H. Low priority group in the back. So what is this? It's also S. You see how these are the same? They have the same name and they're both S. You can get the mirror image by drawing the mirror, or you can just switch the projection. Everybody good? That's all reviewed. Which compound gives a chiral product when hydrobrominated with HBr? Anybody? Which one?
For the destination RS, I thought since the chlorine group was coming towards us, wouldn't it go counterclockwise?
Which one?
For the R, so for the one that's
Here?
get out.
No. 1, 2, 3. That's clockwise. That's the way a clock turns, right?
Oh, so it goes with the full of it. I thought it was the stereochemistry. Stereochem thing. Okay.
No. Draw it. Go from the path from 1 to 2 to 3. That way. Here, the path from 1 to 2 to 3. 1, 2, 3. Which way is that? That's not the way a clock turns. That's going this way. That's called counterclockwise. Counterclockwise is S as long as the low priority group is back. If it's forward, you switch it. Your book will tell you, well, you got to change your view. No, just switch it. If it's in the plane, that's when we have to look at it from the side. Unless you just want to guess, because you got a 50-50 chance. But who wants to just guess? Nobody. Answer down here. Which one of these?
The second one from the left.
Second one from the left. This one.
Yes, sir.
Okay. Well, if it's hydrobrominated, where are we going to make cation? Right or left?
Left.
Left. We'll substitute it. That's where the bromide will attack?
Yes, sir.
What would that product look like? Boom, 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 boom. The bromine here?
Yes, sir.
Yes, if we hydrobrominate the second compound, that will be the product. Is that product chiral? Is it chiral? Somebody already said it. No. It's not chiral. Why do you think that's chiral? Do you see a tetrahedral carbon with 4 different things attached?
No.
Is this a tetrahedral carbon? I mean, yes it is.
Yes.
Is it 4 different things attached?
No.
No. Bromine, methyl, ethyl, ethyl. 2 ethyls are the same. It's not a chiral product. Yes, I can show the bromine forward or back. You want to do that? Let's put the bromine forward. And you want to put the methyl back? How about that? It is tetrahedral. Okay? And then maybe let's do the bromine back and the methyl forward. What's the relationship between these two?
They're the same.
That's the same compound. How do we know they're the same compound? How do you know these 2 paper clips are the same? How do we know plane of symmetry?
They touch the same carbon.
Doesn't they not?
What?
Superimposable?
These are the same. Why? There's a plane of symmetry.
They're superimposed.
Question?
Where's the plane of symmetry?
I could ask you this. Where's the lack of symmetry? Let's do it like that. A compound will have symmetry. That's the easiest. Unless it has a lack of symmetry. What is a lack of symmetry?
Carbon.
A chiral carbon is a lack of symmetry. That's why we identify them. So let's do it that way. Do you see a lack of symmetry anywhere? The answer is no, there is no lack. If I were to show you a model, I could cut right through it because the bromine is really right in front of the methyl. Okay? It's really like this. The bromine here and here. Okay? They're eclipsed. It's here and it's forward, and the other one is right back. I can't draw them on top. But they're eclipsed, and the plane of symmetry is right through there. We're cutting right through half a bromine, and we're cutting right through half a methyl, and you got 2 ethyls on the side. Okay? You can do that. But in the end, it's the starting point is where's the lack of symmetry? There is no lack of symmetry. Okay? I can do this 100 different ways, and then the hour will go by, and we will have not made any progress. So I'm just sort of talking. Okay? It's the same thing. You can make models, you can see. All right? This is what a chiral carbon is. A chiral carbon is a site of asymmetry, A meaning no symmetry. Otherwise, it's symmetrical. You have to just, okay, take that. You can prove that to yourself. Okay? Like right here. Where's the H here, this joint back? It's actually right behind the chlorine, because the chlorine's like this and the H is back. And the symmetry here is right through here. We cut right through the chlorine and the undrawn H that's back. Okay? Here it's all planar. Here it's you're slicing through this way, like a piece of bread on the board. Here, no. Okay, let's move ahead. Down here. How do you identify if it's chiral? Right now you identify a chiral carbon, and this didn't have a chiral carbon. So what's the answer? Which one will have a chiral carbon?
The third.
The third one? If we hydrobrominate this, we get... Where are you going to make cation? Right or left? Correct. And that's where the bromide will attack. Everybody there? And the bromide is here? Yes, and the new H is where? There? There's your product. Is it chiral? Yes, we got a chiral carbon. Is it chiral? Yeah. A chiral carbon, yes, 4 different things attached. Bromine, methyl, ethyl, and propyl. It's tetrahedral. We can now show 2 different orientations. Because that right there is a site of no symmetry, the entire molecule has no symmetry. And if a molecule, if something just has no symmetry, like my hand, the mirror image is what? Different. Yes. That's what you have here. You can show two different forms of this, like we did up here. We say that product is chiral. When you make this product, you can make like hands. Make a right and a left version. The other three are all going to be achiral or not chiral. Because what's the product over here? Cation, top or bottom? Top. That's where the cation is, and the bromide attacks, and you get that. Do you see a chiral carbon here? No, that's very analogous to this here, except instead of an H back, it's a methyl. This is the same, but it's not chiral. You can show a mirror image, but the mirror image will be the same thing. Just like the mirror image of this is this, they're the same thing. Okay? Chirality, a couple of types of questions you might see in terms of alkene reactions. Everybody good? I'm hoping you've spent some time on these two questions and made some progress here. Okay, Fischer Projections, very great, good way to show compounds, very helpful. Now, was this RS? We got a chiral carbon here, indicates the star. Fischer projection, yeah. Let's see. I'm over here with the H here, the methyl here. I'm over here. What side's the chlorine on? Coming towards you. It's my right. Chlorine F. That's this in a Fischer projection. These are coming forward. These are going back. With the H back, that's what that means. What we got here? 1, 2, 3. We did this last time, right?
Yeah.
What is this, R? It's R configuration. Is that the mirror image over there?
Yes.
It's mirroring, so it should be S. Because if you look in the mirror, hold your hand up, okay, when you get home. All right? You be my mirror. No. Yes. Okay, you see, if you look in the mirror and the other hand is up, it'll be this hand. But the mirror image, that will be the left hand. Look at it. See? I'm holding my right, but you're holding up your left. The mirror image of right hand is left hand. Mirror image of R is S, okay? I'm not even going to do it. I'm 100% confident the other one's S, as long as it's a mirror, okay? Fischer projection, though, helps us see that. All right. Compounds with more than one chiral carbon. Ready to go? All right, let's get going. How many stereoisomers are possible for the following compound? Well, here's one thing we want to know. A maximum number of stereoisomers equals 2 to the n. How? Maximum number of stereoisomers to the n, where n is the number of stereogenic sites. Number of stereogenic sites. What is a stereogenic site? One in common is a chiral carbon. It's a stereogenic site. I think this Klein book calls it a chirality center. Different name, same thing, yeah. Chirality centers. What does stereogenic mean? Well, alkenes can be stereogenic. Yeah? Is this alkene stereogenic? What does genic mean?
Leads to a stereoisomer.
You should hear genic in, what is gene? Ecology. Genetics. Genetics. The beginning, the genesis. Right? Leads to. leads to stereochemistry, gives birth to stereochemistry. Is the way this compound is bonded together, does it lead to stereochemistry? Yes, because this is trans. Could I have a cis version? Yes, I have a cis version, unless you have stereochemistry. Okay? Is the way this one is built, does that lead to stereochemistry?
No.
No, if it does, what does it lead to? It leads to nothing. There is no cis or trans there. Okay? So this alkene is stereogenic and that one is not. Is this carbon stereogenic? Is the way it configured, does it lead to stereochemistry? Yeah, and we illustrate that because we showed the other option. Okay? But not always. Okay, a chiral carbon is a stereogenic site. An alkene can also be a stereogenic site. Entire alkene. Okay, how many stereogenic sites in this compound?
Two.
Two. We have two chiral carbon, that's two stereogenic sites. What's 2 to the 2?
4.
4. Good job. All right, you got to have math to do well in organic chemistry. All right, 2 to 2 is 4. That's the maximum number of stereoisomers. Can you draw all 4? What does it mean by maximum? Well, sometimes there may be less than that. There'll never be more. Okay? Up here, it was 1. What's 2 to the 1? 2. What are the 2? They're drawn up there. Those are the 2. They came from 2 to the 1. But this is 2 to the 2, and that's 4. Let's draw them. Here we go. Make some room. Make sure you have room. We're going to come across. We're going to come down. Okay. Let's see here. And I need to make room on the board. Let's see here. Boom, boom, boom. How about if we make the OH like that, and make the chlorine also like that? Yep. How about the OH like that? Chlorine like that? How about the OH like this? And the chlorine also like that? Yeah? What else can we do? Okay, well there's 4 different drawings, or is that really 4 different compounds? Well, we need to make sure. Let's keep going. What can we do now? Those are all stereoisomers, but they all have the same connectivity. If you name them, it would be 2-chloro-3-hydroxybutane. Every one of those is 2-chloro-3-hydroxybutane. Same name. All right, how can we distinguish it? How about R and S? Right here, RS. Chiral carbons, different configurations. Oxygen 1. Carbon with chlorine would be 2. Carbon with nothing would be 3. H going back, what is this? 4. Yes, that's R. How about over here? Chlorine 1. Carbon with OH would be 2. Carbon with just H's would be 3. H going back here. So what is this?
R.
R. Yeah, both of those are R there. Okay? I'll give you 2 seconds to do the rest. Here we go. What is this one? R. What is this one? S. 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 And this one? R. R. Okay, we cheated after we did the first one. Everybody agree that that's R, that is? Because the backbone's the same, we just switched the projection. You can check and make sure, but I guarantee you it's, yeah. Okay, there you go. What's the relationship between these? Well, let's start here. This one. Is there an enantiomer up here?
Yes.
What's the enantiomer of RR?
SS.
SS. If RR looks in the mirror, it's going to see SS. Everything's reversed. Let's label these as 1, 2, 3, 4. I don't know if we need to, but RR, where's the enantiomer? One and 3 are enantiomers. Everybody agree? Do they look like mirror images as drawn? Not necessarily. But you know that the mirror image of RR is what? Yes. They are mirror images. But are they different? Everything's got a mirror image. We need to make sure. Okay, here's 2. Is there an enantiomer of 2 up here? What's the mirror image of RS? SR. These are mirror images. And I will tell you they are different. They are enantiomers. This one. Is this going to rotate like to the right or left? Well, let's go back to this. Is this compound chiral?
Yes.
How do you know it's chiral? Because now we got different. We have, yes, we have 2 chiral carbons, but is the compound as a whole chiral?
No.
What do we need to look for? Plane of symmetry. Does compound 1 have a plane of symmetry? Let's see here. There's my backbone. OH blue forward. Green, also, chlorine green also forward. Backbone is black on the board. OH forward, chlorine forward. Is that the compound?
Yes.
Okay, let's look at it like this. Does it have a plane of symmetry? Well, here we go. I can slice right through here. Black methyl, black methyl. But is that in plane of symmetry? No, first off, it can't be, because I got to have another green over here. No matter how it's positioned, if there's a green over there and I'm slicing from here, I got to have a green over there. So, no. How about if I slice right through the blue and the green? Half a blue, half a green. What's the problem there? Well, now I got a methyl on one side and then over here, so that's not a plane of symmetry either. The answer is there is no plane of symmetry. Until the mirror image what's the enantiomer? 3? Here. OH back. Chlorine back, is that right? Black in the plane, OH back, chlorine back, that's that one? Okay. Let's make the blue and the green both come this way. There we go. Are they mirroring? Mirroring? Yeah. Okay. Are they the same? We've already said there's no plane of symmetry. Let's see if they'll superimpose. Blue and the green are lining up. But look. Over here. The blues are lining up, but the blacks will not. If I line the blacks up, then the blues will not. And they never will. These will never superimpose. They're like hands. Another way to see this is to draw a Fischer projection. Let's draw compound 1 in a Fischer projection. Okay, here we go. We have 2 chiral carbons, so instead of just drawing like that, we need to draw 2. And each carbon here is chiral. We have the ground. Let's make ground over here. Chlorine closer to the ground. And 2 chiral carbons vertical to the ground. Typically, you want to put the alkyl groups back. This methyl going away from us, what side's the OH on? I'm going to stand here, my feet on the ground. The methyl going away from me, what side's the OH on? Left. The methyl going away from me, the OH is on the left. These are 2 methyls. Okay? With this methyl going away, what side's the chlorine on? With that methyl going away, the chlorine is on the right. Here is an H. We're drawing the undrawn H's in Fischer projections. For this methyl to be going away, I need to be standing over here, feet on the ground, and looking through here. Here's the carbon, the methyl's going away. Chlorine's coming out, it's on the right. Here's compound 1 in a Fischer projection. Compound 3 in a Fischer projection. Around here. With this methyl going away, what side's the OH on? I'd have to be standing here, but the methyl will be going away. With it going away, the OH is going back. If I'm over here, back is to my right. Methyl going away, OH is on the right. I'm drawn H here. The other methyl, we need to stand over here. And through here. With the methyl going away, chlorine is on the left. I've drawn H here. There you go. There's number 3 in a Fischer projection. Here's the power of the Fischer projection. It makes it so much easier to see symmetry, planes of symmetry, etc. Look at these 2. What do they look like to you? Relationship. Mirror images, yes. You see how they're mirroring?
So when we're doing artificial projection and we're trying to determine two layers, so we look at the top from for the first one and we look at the bottom.
You want to look look at it with the methyl going. When you look here, how is this methyl oriented? Right here. What does a Fischer mean? Things at top and bottom are doing what? Going away. Okay? With the methyl going away, the chlorine's on the right. That's what that is telling me. How did I get there? Because I looked at it with the methyl going away. Here's the site, and here's the methyl. For it to be going away, I have to be over here. You agree? It's going away. If I'm over here, chlorine is going towards you or behind the board? It's dash, it's behind the board. If I'm over here, behind the board is on my left. I see a methyl going away and a chlorine on my left. I'm looking at this one. Methyl going away, chlorine on the left. I'm drawing the same thing I see over there. Here you go. These are enantiomers. We see it better. Here, you can also see plane of symmetry. Do you see a plane of symmetry here? And it's easy. You have to trust that it's easy. Is this a plane of symmetry? Obviously not. If that's an OH, I need an OH here. It's not. Is this a plane of symmetry? Don't draw on your paper. No. If I got a chlorine here, I got to have a chlorine here. That's the only two places to look in the Fischer projection. Trust me. The answer is there's no plane of symmetry. If there's no plane of symmetry, what do you know about the mirror image, which is his? Different. And there you go. You just assess everything. These are mirror images that are different. What do we call these? Enantiomers. 1 and 3 are enantiomers. Now I can go back to this. Since there's no plane of symmetry, that means it's chiral. The mirror image is different. Since it's chiral, it will rotate PP light. Back to the question, will this rotate PP light to the right or left? We don't know. Right with me? But we do know this. One of these will rotate light one way and one the other. One of these is thus D, one is L. I don't know which is which, but can I call this a DL pair? Pair of enantiomers is also called a DL pair, right? I don't know which is D and which is L. We'll have to do the experiment. But one is D, one is L. Okay. 2 and 4 are also enantiomers. You can do the same thing. Need to work with these a little bit. We'll talk more. I'll even maybe show you a trick or two as we move forward. If you're not ready for the tricks yet. What's the relationship between 1 and 2? Are 1 and 2 enantiomers? No. Because enantiomer RR is SS, not RS. So what's the relationship between 1 and 2? Are they stereoisomers?
Yes.
Yeah, they have the same connectivity. They're both 2-chloro-3-hydroxybutane. Are they the same thing? No, they're not the same thing. One is RR, one is RS. So what's the relationship? Diastereomers. Diastereomers is kind of a default group. If they ain't enantiomers, but still stereoisomers, they're diastereomers. Diastereomers are stereoisomers that are not mirror images. Now, enantiomers have identical properties because they have the same sort of configuration. It's just all reversed. Diastereomers have very different properties, usually. Diastereomers can have very different melting points. This gets to the lab last week. A week and a half ago. DL versus meso. Okay? Diastereomers. The definition is all throughout your notes and in the textbook. Stereoisomers that are not mirror images. What's the relationship between 3 and 4? Diastereomers. Okay? Okay, we need to move ahead. Basically, on the board here, you have 4 different stereoisomers. You've got 2 DL pairs. 1 and 3 is a DL pair. 2 and 4 is a DL pair. Other relationships, such as between 1 and 2, they're diastereomers. Diastereomers have different properties. Let's repeat number 1 above using the following compound. How many stereoisomers possible down here? I have 2 chiral carbons. 2 to the 2 would be 4 max. Okay? OH. You need to redraw these on your paper. I'm just going to erase. I'm just going to change the chlorine to an OH. The RS will be the same because OH and chlorine both are going to be high priority on that carbon. Starting Wednesday or perhaps Friday. Wednesday,
You need to have the alkyne handout that I sent by email to you on September 16th.
okay. Okay, there are the 4 we can draw. Question here is it really 4 different compounds up there?
No.
Well, that was quick and good. How do we know? What's the relationship between, we got an RR. What's the relationship between these 2, 1 and 3? Those are enantiomers. What's the mirror image of RR? SS, check. Same or different?
The same.
What's the relationship between these 2? Those are the same compound. Same compound. Let's draw number 2 here in the Fischer projection. We'll make this be the ground. With this methyl going away, what side's the OH on?
Left.
Right. Methyl going away, OH is on the left. With the other methyl going away, what side is the OH on? This methyl going away. This one's closer to the ground, right? That one's closer to the ground. With this methyl going away, what side is the OH on? It's on the left. Undrilled H is here. This is number 2. There you go. There's number 2 in a Fischer projection. Is this compound chiral?
Yes.
What do you see? Do you see the plane of symmetry? Where is it easier to see the plane of symmetry, in the perspective drawing or the Fischer? Fischer. That's why the Fischer is so powerful. Everybody see the plane symmetry? Yeah? Trust, there's no tricks here. The top is mirroring the bottom. You don't have to worry about how's it projected. It's that simple. Number 2. Let's draw number, what did we say, 4? Draw in a Fischer projection. We'll make this to ground. With this melted going away, what side is the OH on? Right. Top melted going away. OH is here. Bottom melted, with it going away, what side is the OH on? Right. Here, this is number 4. Are these mirror images?
Yes.
You see how they're mirroring? Yes. What's the mirror of RS? SR. They are mirroring. But here's the question. Are they the same or different? We already said they're the same. How do we know they're the same?
You can superimpose them.
Because something that has an internal mirror plane, what does that tell you about the mirror image? Tells you it's the same thing. That's why the paper flips. Are these the same or different? Or are they the same because it has an internal mirror plane? The mirror image will be the same thing. Hey, I got a compound with an internal mirror plane. The mirror image is going to be the same thing. Will they superimpose? Yes, because all you got to do is take this one and do that, and it will sit right on top of the other. Because an OH is an OH. Yes, if we start this one, it will then be up here, right? Right? OH down. If I just do this, now the OH is up. All I got to do is just do that, and it'll be the same thing. But the fact that it has a plane of symmetry tells us that we can manipulate like that. Okay? It turns out that 2 and 4 are the same. What do we have here? We have a DL pair. And then we have this. How many total compounds on the board? 3. Only 3. Not the maximum of 4. What do you want to call the compound over here that's drawn twice? It's called meso. Meso is a compound that has chiral carbons, but it also has a plane of symmetry, and thus it's not chiral as a whole. So in this case, down here, there's only 3 stereoisomers. You've got 1 DL pair, that's 2. Pair of enantiomers. Yes, because 1 and 3 does not have a plane of symmetry. They will not superimpose. But 2 and 4 will superimpose. It's the same compound. There's only 3 on the board, and we call that one compound that's drawn twice a meso compound. Okay, we're out of time. We'll try to pull the loose ends together. Lab report due when you come to the lab this week, right? So we can see how we're doing on Wednesday. Pull this together.
What is the Sidefinder one people? Thursday?
Yeah. Mike can make that do Monday. Yeah. I forgot to mention erythro and threo. We need to go back and do that. Erythro and threo. Have a good day, guys.
The Sidefinder.
Oh, yeah. I know what I mean. Yeah.
I know, that's why I call it that's why I know it as. Mastering genetics. It doesn't have the same, it doesn't have the same ring. No, I like mastering bio. It brings back, yes, we have a connection.